So that's what it should look like. Everybody takes their data, gets it out, okay? And there are links between them. In the ideal world, those links are really the triples, are really these arcs in the graph directly. So we say, my book in my publishing catalog was written by this guy. Someone else has already identified him, so you use that URI to say that guy. Okay? In the less ideal world, you don't. No? Either you come up with a whole new URI yourself, which often happens, or things were a bit shaky before you started. There were already multiple people using different URIs for people and things. Okay? So you have to go about aligning that stuff. Now, a bit of our experience. You're probably used to seeing this cloud diagram, probably a bigger one than this, with loads of bubbles. Okay? Each one of these is a data set that someone has got out. Okay? Each arrow in this case is some interlinkage between these things, so some shared identifiers. And the good news is, it looks more and more spider-like every 6 months, spiderweb-like, sorry, every 6 months. More and more links between these data sets. But there's work to do in consuming this stuff. Okay? We have two, I want to say cullings, but that's about a sort of awful word at the moment. We have two harvestings, that's positive, harvestings of this data together to show people you can align this stuff and you can make sensible queries over the joins between these data sets. Okay? One of them is general purpose, and it's a bit of just a demonstrator. We call it FactForge. We pick up some really cool stuff that I love to work with. Marco mentioned DBpedia. It's Wikipedia in RDF to some degree. My favorite is right up there somewhere, up to the top, music brains. Loads of data about music, which is my passion. Geonames, great for geography. Okay? If you want to say this meeting is in Jersey or specifically Hoboken, that was it. Sorry. Jet lag. Yeah. If you want to identify Hoboken in New Jersey, in the United States, all of those identifiers are right there. Really interesting one, Freebase.
Frank Sinatra was born in Hoboken, I think.
See, that's the kind of thing that DBpedia tells you.
And because you will now remember, because you're a music fan.
So, yeah, let me quickly mention Freebase, because one has to in this situation. Big data sets, wiki-driven, people deliberately making and editing lots and lots of data. Got bought out by Google, as you probably know. We got some nice tools out of it, and I'll mention this again later, for getting your data out of spreadsheets and tables, a tool called Refine. More recently, Google harnessed that data set to disambiguate search. Okay? Every time you go to the Google search box and type something in, and you get interesting stuff over on the right-hand side that says, our primary idea, what you're talking about when you say William Shakespeare, is this dude with the beard in a picture who was born in, not doing this very well, something.
Stratford.
No, Stratford I was looking for the year. Can't remember. Oh, he's not actually known for Shakespeare very well, so part of your partially defined data. Anyway, they use the linked data in that graph of Freebase to say, we think this is who you're searching for, okay? But some of those searches are ambiguous, because all you've done is put in text. So what not everybody quite realizes yet about the knowledge graph is that if you search for, the first example I saw was Mona Lisa, gives you the picture, Joconde, in the Louvre, so museum data in this knowledge graph. But also down the bottom it says there's another entity with that name, Mona Lisa the film, 90s film. And try this in Google if you haven't tried it. You go click on the film and your search results change. Okay? Because you've disambiguated your plain text search, told it you mean the film, and Google do their best to give you search results about the film rather than about the picture. Okay? So Google capitalized on this data set called Freebase and call it the Google Knowledge Graph. They give us quite a bit of what they do. They've invested in this massively. They don't give us all of it. My current gripe is, according to this lovely data here, my former Prime Minister, Margaret Thatcher, is still alive. You go to Google and type Margaret Thatcher, the knowledge graph tells you she has a date when she died, and she died at the Ritz in London. Okay? But if you go to Freebase, they still don't give us that. Okay?
Don't tell the Irish.
I'm Northern English. I have as strong feelings as the Irish do. Another announcement, kind of 2 weeks ago, Microsoft are doing the same thing. You go to Bing, you search, up comes this disambiguation on the right-hand side, and it's driven by something called the knowledge graph, or Microsoft knowledge graph. Yeah, they're really good at picking original names when they copy things. What I love about that is Microsoft's graph database to store their knowledge graph is really compliant with some of these standards. You can put RDF straight in, and you can query the thing in Sparkle. Okay, I've forgotten the name of it, Baz. Trinity, thank you very much. Okay, so back to the point. We took these data sets quite a long time ago. I'm giving some slides that are out of date because there's going to be a new section of this in what we call FactForge. But we take them, we look at the interlinkage, we improve it, we improve alignment, okay, in the vocabularies used to make it easier to use these data sets together through some of the techniques that I'm going to talk about using the semantic technologies, using especially ontology functionality. Okay. Yellow stuff is another harvesting from this cloud of open data sets. And this is part of the reason that I wanted to give this presentation, because we were talking with Wiley this morning about interest in these kind of biomedical data sets that are out there. How do you identify proteins and drugs and pathways and the relationships between them? There's some very nice data sets, but they need some cleaning up and alignment to use together. How do we do it? Well, ontologies are one tool in the armory. So I'm going to skip the size of those things because that's out of date. Let me do a bit of promotion. Hope you don't mind that. I work in a project, a European project, that's focused on educating people about linked data and linked data practice and how that interacts with data science. Part of the reason to tell you that is you're very welcome to come and see all of these slides, which from now on are Creative Commons licensed, or watch me presenting them if you happen to enjoy that. I doubt it. They're delivered first as a live webinar, and we deliberately do it in the afternoon in Europe, so at least on the East Coast, it's an accessible time to you. So on Monday at 9 o'clock in the morning, I believe, in Eastern time, I would talk about some of the tools for getting your data out, the prerequisite to this, which fits into this scenario again. I said I'm enthusiastic about music, so everything in this project is based around different uses of semantic technologies and how they could apply to music. Okay? What I'm going to talk about right now is up here. Now, mapping, alignment, interlinking, a little bit about cleansing. On the webinar on Monday, I would talk, as I did at the London StemWeb meetup, about things like transforming relational databases into linked data. Okay? Also about the Refine tool that I mentioned came from Freebase, from MetaWeb, through Google, and a little bit about entity or concept extraction from plain text and the tools that you can use to do that. So, introduction to getting your data out. If you would like to watch it on Monday, right now, without further ado, I'll talk about this stuff using the Euclid slides. Okay, so here's the specific scenario for alignment, which is part of the, what we did in FactForge. You have some very nice data sets for music. Okay? They come from Music Brains, whose primary source was, I don't know if anybody remembers CDDB, when everybody was ripping their, right? When everybody was busy ripping their CDs to MP3s, back in the day of sharing them in Napster. There was a nice service for sharing this information about tracks and albums and artists. they sold out. So Music Brains came along and said, let's do it with open data and with a wiki. Okay? So they built, to start with, a nice database full of track and album information, and then started to get more into modeling music and labels and membership of people in bands and all of this cool stuff. Okay? Now, a lot of that's also in Wikipedia. So pick your favorite album, it's probably got a Wikipedia page, and the artist's probably got a Wikipedia page. Mine isn't. It's too obscure. No? Some of you might be shaking your head right now. My favorite artist isn't in Wikipedia, or at least I listen to several artists who are not. Okay? So we have disjoint data sets. You pull out Wikipedia into DBpedia, and you have some identifiers. Music Brains has more identifiers, but you talk to, especially to cultural heritage people, and they say, it's all very good for pop music, but there's lots of musicians that we know about because we have really mentions or maybe scores in our collection that just don't make it onto CD. So they haven't gone into Music Brains. Some of them might have gone into Wikipedia because scholars are interested in documenting their subject area. Some might belong in different data sets. Okay? So different data sets are rich in different parts. For the definitive idea of how many times has Sgt. Pepper's been released in each of the countries of the world, and on what format, and which signal did it come from, the original mono, okay, the stereo, the 24-bit remaster, you can't beat Music Brains. Okay? For the biography of the Beatles, Wikipedia can actually be pretty strong. Okay? But for your more obscure artists, you go to museum collections, for instance. And we want to put this stuff together, okay, and be able to form uniform queries over the top of it. So we want an integrated data set. And unfortunately, that doesn't quite happen for free. Okay? Turning it into RDF is a fantastic first start. Okay? Instead of having Music Brains, Marco heard at length in London about how many tables there are in the relational schema for Music Brains. They have a big Postgres database. Okay? You want to put more stuff in there or integrate it with something else using relational technology, pretty awful. Okay? Another data set might be relational, might be something that you pull in XML through an API, might be something you pull in JSON through an API. Difficult to put them together. Turning them into RDF is a good first step in the sense that you can pick up a triple store and load all of that data together. But it doesn't mean that the identifiers are aligned. You might have multiple identifiers for the same thing. And it doesn't mean that where they overlap, okay, where Music Brains say that Paul McCartney is in the Beatles, and where DBpedia says Paul McCartney is in the Beatles, they don't say it in the same technology. In the same terminology. Okay? So you have to align these things at the instance and at the vocabulary level to have a nice data set so that we can do the kind of things that people are really excited about doing now with Sparkle. Sparkle 1.1 has introduced lots of aggregates and groupings. Fantastic to build applications on top if you've got clean data. Awful if you haven't, and you ask how many people are in the Beatles, and first it's, well, which Beatles? And then even if you get the Beatles together, it's 16 people, because we've got different representations for Paul McCartney. Okay, so here's kind of what that looks like. Bit of Music Brains data, and believe me or believe me not, you can resolve the URI, because it's linked data, and find out the top identifiers for the Beatles, okay, in Music Brains. And on the right, we have the Beatles in DBpedia. A bit easier to tell that. Okay? But they both of these URIs represent the Beatles. Okay? And as far as you know, having loaded these data sets, well, they're distinct resources. They've got distinct URIs. Similarly, we share some properties. I don't have many there, but trust me, DBpedia's got a label for the Beatles, a name, and there's one over here. And then there's some stuff where one is richer than the other. I don't believe, but don't quote me, don't film me, that Music Brains knows that the Beatles were founded in Liverpool, but that's the kind of biographic detail that people put into the Wikipedia and we can pull out in DBpedia. Okay? So smushing this together, as the term we often used, I don't know what information architects call smushing.
Smushing.
Information integration is what I first called it, but then smushing sounds so much nicer. Let's tell that these are the same resources, but also that the shared descriptions are actually the same thing as well. So that's integration. What we want is to be able to query, for instance, this really rich data set in Music Brains using DBpedia ID. I should have sort of pointed that out. The big spider web of all these data sets. People love, for better or worse, interlinking through DBpedia. Okay. DBpedia has a lot of IDs for things. Why? Because people spend centuries editing that information and agreeing on pages about things, and each page title becomes a URI. Okay. It's very rich for identifying things, and it's something that you can go and look up in Wikipedia. And in many languages, extraction of a DBpedia from Wikipedia, you have URIs that are pretty readable. Okay? And people like that, for better or worse. What we want to do is make a query like this, where we combine information from different sources. Okay? Ideally, as I'll show, I would want to use the music ontology, a very rich model to talk about music, to query all of the things that are attached to the Beatles. But here I'm deliberately showing we want DBpedia to tell us the genre, because Music Brains don't concentrate on that, but we want music ontology to tell us who's the member of the Beatles. Okay? This only works if we know there's one Beatles, and both of these data sets are talking about the same thing. Okay? And that really works. Okay? You get the answer of the genre there. Sorry, you get the membership as well. Missing the slide. Apologies. How? Here's one. Here's the revised story of how that works with semantics. Okay? Which is the query language that we wrote that query with that says, I'm talking about the Beatles according to Wikipedia and DBpedia. Give me the genre and the members. Okay? The language that I used to make that query called Sparkle, the something protocol and RDF query language. Sorry about the something.
It's recursive.
It could be recursive, it could be simple, or it could be semantic. Depends which day of the week it is. Hi, I didn't see you come in.
George actually is, George London is actually based here in New York, and he helps with the meetups. And he has just released a music database. I guess that's public, so I guess you have something to talk about.
Let's talk about that later.
Exactly this information.
Based on Music Brains.
Data sets in this reconciliation process.
Okay.
So
Good. Yeah, so the query language. Something, protocol, and RDF query language. Let us write that query. And that's all it used to do, is let us write queries. Now it's nice, it lets us write better queries. Okay? Relational database people said, why can't we do aggregates and grouping and subqueries? And lo and behold, Sparkle 1.1 does it. Okay? XML people said, why don't we have built-ins to deal with the XML data types you're committed to? And lo and behold, you somewhat have it. Graph database people said, why do we have to only investigate links directly and construct long paths ourselves and no long very strict paths where we name every step? And lo and behold, we have an expression language for paths. Looks a lot like, I'm saying a lot these days, regular expressions over paths. You know, what you do to characters in a regular expression, you do with the connection between things in your graph in Sparkle 1.1. Okay? It's also got an update part, which is handy. Have a standardized way to put data in, take it out and change it. Some cool stuff like federation. Okay? Run your Sparkle in more than one place, in more than one engine. And it has something called entailment, which says most decent triple stores have been aware of the way that you express your vocabularies in RDF schema and the web ontology language, okay, respectively RDFS and OWL. Okay. Most triple stores have been aware of those things and have allowed you somehow to query over inferred information from your data set, not just explicit information. Okay. Why? Your vocabularies give you a model, okay, for the kinds of things, the classes that you're talking about, and the relationships between them that we call properties. And they have semantics. Okay? When you relate things certain ways, when you classify things certain ways, you can tell more relationships and more classifications as a result. Okay? The model for that semantics is basically triples in, more triples out. What were you saying, Matt, about it being like investing in a bank? Yeah? If you hide your money under the bed, you just pull out the same notes later. If you put your money in a bank, one hopes, perhaps one has a little less confidence in recent years, that what you get out is more notes. Okay? So, the same thing, somehow, with a triple store. You build a model for your data in RDFS or in OWL. You put some triples in with those triples that define your model, and you get more triples, and when you query, you can see those additional triples, the inferred ones, as well as the ones that you put in. Okay? All the time I was saying somehow, because I was talking about how things were. Now Sparkle 1.1 says how. It says, if you have RDFS, or if you have some of the nice forms of ontology that OWL will let you build, then this is how the query should expose all of this extra money, value, you have for what you put in. Okay? Nobody disagreed with that. Hey, it said riff on the bottom here. Chris isn't here. We had lunch with one of the guys responsible for part of that. So I'm going to tell you first about what you can do with RDFS. How long have we been talking, Marco?
We have another, actually, 50 minutes.
Okay, no worries. I'll tell you quickly about I'll tell you about RDFS and I'll tell you quickly about OWL. Okay. On the technical side, we have a lot of rules to tell you if you use certain of these modeling functionalities, here are the triples that you get. Luckily, under Sparkle, you don't have to worry about what these mean, because these are mapped in this entailment regime underneath Sparkle, so your triple store will do it for you in a standard way. So, on the practical side, you put in a triple that says, for instance, this member relationship that's going to relate the Beatles to Paul McCartney, it has something called a domain. It says when you use this relationship, the thing that's the source of the relationship, the Beatles in one case, the Stones in another, should be in the class, the grouping called music group. Okay. So anything that's got a member in the music vocabulary, the music ontology, the source of that membership relationship should be in the class of music groups. Okay. On the one hand, that tells you how to use this relationship if you're explicitly making data. Okay. If you want to know how to express the relationship Paul McCartney's in the Beatles, this tells you which way around it goes. Okay. The Beatles go at the subject, and Paul McCartney goes at the object. But in inference terms, it says whenever you put in a triple relating things in this relationship, then the Beatles become a music group. So when we query what are the music groups, without inference we get potentially nothing, but with, on this graph where we've got these four memberships, the Beatles are now in that class, so it's queryable. Now our query says what's in that class, and now the Beatles are in it because we've used that relationship that way. Okay, range is the opposite. It says what's on the other side, or those things that are on the other side, what kind of things are they? What class do they go in? So we say that they're agents. A little bit weird. Again, we discussed this in London last week. They're not necessarily people because there are dogs and robots in bands. Okay? We checked it on YouTube afterwards. We found several bands that have robots in. Okay, so if we exercise this, again, same relationship, the same way John, Paul, George and Ringo are in the Beatles, without inference we ask who are agents. We haven't modelled any, but with inference we say John, Paul, George and Ringo are agents. Okay? They have agentive behaviour like playing instruments and singing and things like that. Okay? Don't know that they're people, but we might be able to infer that from other things as well. Okay, so getting on to something that's useful for alignment. This subproperty of relationship says that one property is more specific than another one. Okay? But the specific one implies the more general one. Okay? So it says if I'm a singer for a band, then I'm a performer for that band. Okay? By inference. So if you say John, Ringo and George are performers for the Beatles, but Paul is specifically a singer, at least in a certain context, querying without inference, we just get the three guys who directly have that performer relationship, but with inference, you get the extra relationship, okay, and query back for all four of them. All four of them are performers for the Beatles, three because they are directly, one because he's a singer, which is a kind of performer. Okay? Now that's within one model. Both singer and performer are in the same vocabulary, in the music ontology, but we can use that where different data sets have used relationships that have this characteristic. They're not exactly the same, but one of them implies the other. Okay? So if we have, in a crude case, a database full of singers, and we wanted to query that alongside something generally about musicians, you could use subproperty for alignment. Okay? If you had a database full of specifically book authors, okay, with a relationship to say this is an author of this book, but you also have a wider catalogue of creative works as a publisher, okay, you might want to align these two together by saying every author is also the creator of a creative work. Okay? So we can do some alignment with this in RDFS. And the other form of that is subclass. So we can talk about the relationship between two things, a piece of music and the singer on it, or the band and the singer in it, or the book and the author. Or we can just put things into classes. We can say, these group of resources represent authors, book authors. Okay? And then generally talk about people who've what's a class? Creative people. Okay? Or here, we could say, we do say, music group is a subclass of music artist. Okay? Music artist is the more general concept than either individual solo performers and groups. Okay? So if the Beatles are a music group, they become a music artist. Okay? So similarly, somewhat useful for alignment. If we put things into a specific class in one data set and have a general class in another one, okay, we can say all of the things in that specific class become part of the general thing by putting the data together and making a subclass statement between those two classes from different vocabularies. So, not to belabor the point, but the Beatles are a music artist. Now, I want to say two things about RDFS. One is, there's no idea of inconsistency or contradiction here. Okay? This isn't so much an alignment point, but it's worth reinforcing this with people newly adopting this technology. What looks like a logical contradiction, perhaps through mismodeling here, we can't pick up on this just using RDFS. So if I don't like this property, it's difficult to read which way around it goes. Do we say Beatles member Paul McCartney? Paul McCartney member Beatles. If I haven't checked the vocabulary to know, I might say Paul McCartney explicitly is a solo music artist, but try to say he's a member of the Beatles. I've mismodeled because I've used the property the wrong way around, but the inference I get back says Paul McCartney's a music group, okay? And though all common sense says nobody is a solo music artist and a music group at the same time, we don't have means to say that shouldn't happen in ODFS. That's one motivation for OWL. Okay? In OWL we can say, no, you can't be in both of these classes. Okay? There's also stuff that RDFS just can't do in terms of inferences that we want. We can say Paul McCartney made the song yesterday and that he knows Ringo Starr. Okay? And among the things that we can infer from that Paul McCartney, Bjorn, is an agent. More specifically, Paul McCartney is a person. Good to know. We can know that Ringo Starr is a person from that. But we might want to know that yesterday's creator, in a different vocabulary, but a very common one, the doubling call one, often used for metadata, is Paul McCartney. Okay? Why can't I do that? Well, because not only does Paul McCartney, having made yesterday, not only is that neither more specific nor more general than this statement, it's actually equivalent to it, okay, it's also expressed the other way around. And this is a problem with RDFS. If we want to imply one from the other, well, we can do it one way with subproperty of, it's only the same relationship in the same direction. We can't say it holds the other way, a different relationship holds the other way around between these two things. Okay? Similarly, in the same property, we've said Paul knows Ringo, we might want to infer Ringo knows Paul. Unfortunately, RDFS just isn't powerful enough to do that. But OWL is enough to say both of these things. Okay? So this is a way to build vocabularies, a way to describe relationships in properties, and kinds of things in classes that lets you more powerfully say what you infer by using that model, okay? And to some degree what shouldn't happen, what would be inconsistent. So I'm going to skip forward a little bit and give you some interesting ones. So here's an alignment one. I said some things are just the same relationship said two different ways, with two different URIs, because two different people modeled them. Okay? So an alignment that you might need to do is to say, when this holds between two things, this holds between two things. Okay? When I say in a music ontology that Paul McCartney was in the Beatles, okay, then I can query using DBpedia's relationship for membership, who was in the Beatles, and I ought to just be able to get Paul McCartney, because those two relationships are the same thing. Okay? How do we say the same thing? It's just another triple. We say that band member, which is DBpedia's name for this relationship, is an equivalent property to member in the music ontology. And then whichever one's stated between two different data sets, you get the other one as well. Okay? So we write a query, for instance, which says who's a band member using the DBpedia idea. Without inference, we get nothing when we have this lovely rich graph from Music Brains. With inference, we get John, Paul, George, and Ringo. We're in the Beatles using that other vocabulary. Okay? The beauty of Sparkle 1.1 is it tells you, if you have said this, if you have this triple, with these four triples in this graph, a compliant query endpoint will definitely give you these results, will definitely tell you John, Paul, George, and Ringo. Okay? So if you have, that's kind of nice, you can query with someone else's vocabulary. Even better, you've got two data sets that overlap somewhat. Some have memberships of pop music, stuff that's been released on even broader, things that have been released on CD. Another data set has medieval artists who put them all together and query over the top and do counts over the top, and now everything makes sense. Okay? There's only one Beatles, the Beatles count once, the Stones count once, and some medieval guy who I can't name only counts once. And whichever vocabulary we're comfortable with, you query it, and you get the same results. Okay? That's what alignment is all about. Didn't want to stress consistency too much, but you can also say two relationships can't hold at the same time. Okay? You can't work for someone and supervise them at the same time, for instance. Okay? So it is important for alignment somewhat when you're dealing with quality of data and whether you've made the correct alignment to be able to check these things that we've said about these two vocabularies. If you look at the data, is it consistent now? Or are there contradictions among it? Okay, so you might want to explicitly say some of these things can't hold at the same time, and we can do that. Now, we've got about 5 minutes, right? Let me cherry pick these. The one that I most want to tell you about, I think, is transitivity. Okay? So getting into what extra you can do with reasoning, I motivate with geography is a great example. Okay? I said, right now, I have a relationship via this meeting with Hoboken. Okay? I don't know that so well. I know that I've got a relationship with New Jersey. Okay? People at home just know I've got a relationship through this meeting with the US. If I just want to say, I'm at this meeting in Hoboken, and bring in a data set like geonames, okay, I can infer through Hoboken's being within New Jersey, being within the United States, those things. Okay? Because if Hoboken is inside New Jersey, and New Jersey is inside the United States, Hoboken's in the United States. Okay? Taking that inside what we call parent feature property and making it transitive, okay, means I can just ask, that meeting that Barry's at, what's it in? Okay? And in, no matter how many times it's nested, okay, will come out in the answers. So people get what they want. Well, someone who wants to come see me can find out I'm in Hoboken. Someone who's generally interested in where I am this evening can find out I'm in Jersey, and Mum at home can find out I'm in the United States. Okay, that is property axioms. Very quickly. Oh yeah, another great one, transitivity, genre, just to bring back to music. Subgenre of a subgenre of metal, subgenre of rock becomes a subgenre of rock. Any more for any more. Inverse. This is really a good one for alignment. Okay. I said the music ontology is a bit strange. I love it. I use it all the time. Okay. But it reuses, according to the principles, other vocabularies. It doesn't say, or it doesn't introduce a new relationship to say someone made an album, okay, or someone made a track on an album. It says vocabularies already exist. Okay? So the someone goes in a class called folk agents. Okay? Concomitantly, it says how you say that they've made something, you use a property called made, in this vocabulary called fov, standing for friend of a friend. And then it says that thing that they made, the album or the track, has a title. Okay, fov doesn't give things titles, it only gives things names. So now we use the doubling call. And we say the doubling call has a relationship that says works have titles. Okay. All very noble to reuse things like that. The problem is, having used both fov and doubling call, okay, they overlap. We didn't have to say fov made is the relationship between a person and an album. Doubling call says that works have creators. Okay? Having made something and having created it are equivalent, except that those things are the other way around. I make something, but something's creator is me. Okay? So when I want to align those things So I can say, I query using the doubling call, because music's only part of my catalog as a publisher. Okay? I've got books as well. Okay? So I uniformly say the metadata for my creative works is doubling call, it's stuff librarians tend to love, and I query using doubling call. But that music stuff that I brought in kind of breaks it, because it uses made from the both vocabulary to link people to their creative works. Okay? The way that I align those things is to say that made is the inverse of creator. Okay? So it's exactly that. If the Beatles made Sgt. Pepper's, then Sgt. Pepper's creator was the Beatles. Okay? So the last, as far as I can explain it in the time slot, the last bit of alignment is to say not only do we share some instances, okay, that we need to align, do we share some properties that really mean the same thing and some classes that mean the same thing, or sometimes one is more general than the other. Okay? The last bit is to say sometimes they're the same relationship in these different data sets, but the other way around. Okay? Then I have a whole shtick, which I'd love to talk to you about at some point, but you're welcome to see it in the webinars or in the recording of those or the slides, about how, having loaded all my data, made these alignments using OWL that I know now I can query through in a standard way, how do I use queries to check that things are kosher now? Things are where I expect. Okay? I want to make a query that says, okay, I believe that I now can use creator to find all of my creative works in my catalog. But is it true that everything that's got a creator has a title? Okay. This is one of the queries that I'd like to do. Say, is there something that was created that doesn't have a title? Again, Sparkle has got much stronger here in these negated things. So testing the quality of my alignment to make sure that now I can query across all of this stuff and it's well aligned is, I hope, an interesting topic. But I'm going to have to finish there, I think.
Well, I think that we still have some time left, but probably it's a good time to take some questions.
Absolutely.
And then we take the answers. So thank you very much, Barry. So this was almost an introduction to RDF and the semantic web. And there's so much more to discover that we only have half an hour today to discuss this. But I take some questions from you.
It's more of a comment than a question about the very last thing you talked about, which is the topic you didn't talk about, but about basically quality checks with Sparkle. The folks at SwissApproach, that keep track of all that, I guess about a year or two ago, I'm not sure when it was, wrote a set of consistency rules for all of SwissApproach, which is a pretty seriously large data set and pretty complicated, and managed to greatly increase the quality of the data by using exactly the strategy you talked about. Yeah. And if it was a Sparkle 1.1, it would be really hard to do that in Sparkle 1.0, or maybe impossible.
Absolutely.
So this strategy works, and it works to scale, and it works on real data.
Yeah, yeah. And it's really the combination of the inference through ontologies and the power of the query language now. So equally, Catherine Dentler has a nice paper, also in this similar kind of area, on finding with UMLS, how is this thing redundant?
Oh, that's interesting.
First you need enough reasoning to encode what doctors mean by this actually is the same condition as this one. And then the power of querying over that to say, okay, so how many of these things are wrong? Which ones do we still have to work on aligning or improving?
In fact, I've spent my afternoon with my client this week doing exactly that. We've got our data set, we have our quality things, and okay, I now need to do basically unit tests and I'm running on Sparkle.